Hi, my name is Jackie Sullivan, and I'm the Associate Director of the Rotman Institute of Philosophy. I'm actually Associate Director of Research and Knowledge Mobilization, and it's my pleasure to welcome you to our October lecture series that we're doing in collaboration with the London Library. Our theme for this month is time and memory, and we're going to have 4 talks every Thursday in October from 7 until 8:30. And our talks are going to include a philosopher of physics, a historian and philosopher of science, an art historian, and a cognitive neuroscientist who will all be talking about different issues in the broad theme of time and memory. So without further ado, I want to introduce my colleague Francesca Vidotto, who's going to introduce our speaker for this evening.
Thank you, Jackie. It's my pleasure to introduce Emily tonight. I'm here to represent the philosophy of physics at the Rotman Institute. Emily joined us a year ago in our group. Emily is originally from New Zealand, and actually Canada was her first stop in her superior education. She did a special master at the Institute for Theoretical Physics, the Perimeter Institute in Waterloo, and from there she flew to England, first to Oxford, where she did a master in philosophy and physics. I think getting the best thesis of the year there. and then she did her PhD in Cambridge, working on the subject, officially at least. Of course, her interests are much wider, but the official topic of the thesis was quantum information. That is something that these days you may have seen on the titles of newspapers, because quantum information is the broad field on which the last Nobel Prize for physics has been given last week. So there was the prize was related exactly to the kind of questions that Emily has addressed during her PhD. So there are questions in the foundations of quantum theory, but of course questions in physics are never really just in a compartment. We talk about the fundamental structure of matter that behave in a quantum way, but then this raises questions that are related also with the structure of space-time, because, for instance, the theory raises questions regarding causality, and this is what tonight Emily is going to talk about. So I don't take more time, and I leave the floor to Emily.
Hi, everyone. Thanks very much for coming, and thanks to the organisers for the invitation to be part of this very nice series of talks. So the question I want to address today is, can the future influence the past? And you might well be inclined to say the answer is obviously no, because it's a sort of very fundamental fact of our existence that the actions we take now can have an influence on the future and not the past. And indeed, no matter how much we may regret things that have taken place in the past, there is unfortunately nothing whatsoever we can do about them. But recently, some physicists have begun being interested in the possibility that quantum mechanics might in fact show us that there exists some kind of retrocausality in the world. So the retrocausality just means causation backwards in time. It means events now having an influence or causing things that happen in the past. So what I want to do in this talk basically is first explain why some physicists think that quantum mechanics is showing us that there is retrocausality in reality, and then I'm basically going to assess the evidence for that to decide whether we should really believe that there is retrocausality going on. So here's the plan. So one of the main motivations for believing that quantum mechanics exhibits some kind of retrocausality is because there's a hope that this would help us get rid of non-locality. So I'm going to begin by explaining what I mean by non-locality, and then I'll explain why exactly retrocausality might help us get rid of that. I'll then look in a little bit more detail at the question of what might retrocausality actually look like in a realistic model, and that will lead to some questions like, is retrocausality really local anyway, and is it even a good idea to try to get rid of locality? non-locality. And finally, I'm going to argue that even if you are not trying to get rid of non-locality, there might actually be a different route to retrocausality within quantum mechanics. So, non-locality in quantum mechanics. You may well have heard that quantum mechanics involves something called non-locality, or it's sometimes referred to as spooky action at a distance. Indeed, you might well have read about it in the papers very recently, because this is basically what the most recent Nobel Prize was awarded for the demonstration that quantum mechanics does indeed involve this kind of effect. So what does non-locality look like? Well, it can be demonstrated in the following kind of experiment. Suppose I prepare a pair of particles, and I send one to my friend here in London, and I send the other to my friend in Sydney, and then I have my friends and then I have my friends in London and Sydney perform measurements and compare the results they get. So if we do this several times, it will probably eventually, we can then compare the results, and it may well turn out that my friends will start to notice correlations between their results. That is, the results will be related to each other in some systematic way. So, for example, perhaps they find that they always get the same result. Now, in and of itself, there's nothing particularly weird about that kind of distant correlation. We can produce roughly the same effect if, instead of preparing particles, I just take a pair of socks from my drawer and I send one sock to my friend in London and the other sock to my friend in Sydney, and then they inspect the colours. And under those circumstances, it would, of course, not be very surprising if they were to find that the colours of the socks always match, because I do endeavour to store my socks in matching pairs and mostly succeed. So the mere fact of these kind of distant correlations is not really all that weird. And obviously in this case, what's going on is that we can explain the correlations by the fact that there's a common cause in the past. The socks came from the same pair. It's that common cause which explains the correlations. So here's the quantum twist. A physicist called John Bell studied the set of all correlations which can be explained by this kind of common cause in the past. And he showed that any correlations which can be explained by something like coming from the same pair of socks have to obey a certain inequality. And it turns out that if we perform this experiment with a pair of quantum particles, we can produce correlations which will violate that inequality. And that's what these three people who won the Nobel Prize essentially demonstrated. So what that means is that we can't explain what's going on in that experiment by supposing that there's some relationship that was established in the past when the particles were together. Essentially, it has to be the case that the result that is obtained in Sydney depends in some way on the choice that my friend in London makes about what measurement she's going to perform, or perhaps it's the other way around. It could be that the measurement in London depends on the choice made in Sydney about what measurement is going to be performed. But either way, there needs to be some kind of direct influence that can't be explained by the preparation in the past of those two particles. Furthermore, we can arrange for these measurements to be made so close together in time that there wouldn't be enough time for a physical signal travelling at or below the speed of light to get from London to Sydney in time for the choice of measurement made in London to be communicated to the particle in Sydney. So what that means is that somehow the particle in Sydney seems to just know what's going on with the particle in London, even though there's no possible way that any system could travel in between them carrying that information, given that we have pretty good reasons in modern physics to believe that nothing travels faster than light. So this seems pretty weird. The weirdness is tempered slightly by the fact that these sort of distant non-local effects can't be used to send signals. That is to say, although the result in Sydney in some sense depends on the choice of measurement made in London, we won't be able to use that to send messages faster than light from Sydney to London. The correlations only become evident after several tests when you compare the results. So that's slightly less weird. We don't have sort of superluminal messages flying around everywhere. But nonetheless, this is quite surprising. It's very different to how we thought about physics before quantum mechanics, and a lot of physicists really don't like it. Therefore, ever since Bell proved his theorem, people have been trying to find ways to avoid that conclusion and to say that, in fact, quantum mechanics is local. To do that, basically, we have to deny one of the assumptions that Bell made when proving his theorem. And in particular, one of the assumptions he made is that there is no retrocausality. So if we allow retrocausality, it is quite easy to avoid Bell's conclusion, because basically what we do is we say that when the measurement is made in London, a message is sent forwards into the future carrying the information about what measurement was performed in London, and at some point that message turns around and starts going backwards in time, and it can arrive in Sydney just before the measurement is made in Sydney, and thus it's very straightforward to see how the measurement in Sydney can depend on the choice of measurement in London, because that information has been carried there by a physical signal in the ordinary sort of way, really. So basically, introducing retrocausality allows us to solve the problem that there's no time for a physical signal to travel from London to Sydney, because in fact, we can always get a message from London to Sydney if we're allowed to go forwards in time and then backwards in time. So you might well think at this point, things traveling backwards in time is pretty weird. Indeed, it's just as weird as spooky action at a distance. So have we really gained anything by getting rid of spooky action at a distance by having things travel backwards in time instead? And I do think that's a very valid point. But there are some reasons why physicists think that retrocausality might be not as bad as non-locality in some ways. And we will get to those in a minute. But first, what I want to do is look in a little more detail at what exactly a retrocausal model would actually look like. So there are kind of two different pictures that you might have in mind when you're thinking about what retrocausality is. The first and perhaps the most common picture is the idea that retrocausality involves having two sort of distinct and independent directions of causality. Two arrows, one coming from the past, one coming from the future, and they kind of collide at some point and they cause things to happen in the middle. So that, I think, is what most physicists are probably thinking of when they postulate retrocausal models. But that's not the only possibility. The alternative is what I refer to as all-at-once retrocausality. And to understand that, we have to think about the laws of nature a little bit differently. So often when we think about the laws of nature, we kind of imagine them operating a bit like a computer. So you sort of input an initial state, and then the laws take that state and perform operations on it and evolve it forwards in time. And so we get a history kind of rolling out in a temporal manner. But the laws of nature don't have to work that way. They could, for example, work a bit more like the rules of a game of Sudoku. So what I mean by that is that in a game of Sudoku, you don't start at the left and move towards the right. You can't solve a Sudoku grid like that. The rules apply to the whole thing at once. They simply prescribe whether a whole solution is valid or invalid, and you have to consider the whole thing to make sense of the rules and to tell whether the solution is valid. So the thought is that the laws of nature could work in a similar way. Rather than evolving from some point, they could just prescribe entire solutions at once. So this way of thinking about the laws of nature doesn't appear very much in sort of popular culture, but there is a very nice story by Ted Chiang called The Story of Your Life, which kind of builds in this idea. It's a great story. I would recommend it. Also, the movie Arrival is based on that story. So if you've seen Arrival, maybe you have some vague idea of what I'm talking about here. And if you haven't, again, I would recommend it very highly. So the important point for us is that in this kind of all-at-once picture, in say, a Sudoku grid, evidently there will be correlations between the numbers appearing in different boxes. If you've put a 3 in one of the boxes within one of the larger squares, that means you can't put a 3 anywhere else in that box. And so the existence of a 3 in one point is correlated with the non-existence of a 3 at other points in the box. But evidently, it wouldn't really make sense to say that the 3 causes the non-existence of the other numbers, or vice versa. Sudoku doesn't prescribe an order in which the numbers go. You personally might fill in the grid in some particular order, but other people can fill it in a different order, and their solution is just as good. There's kind of no intrinsic ordering to the rules here. And that's exactly what we would expect to see also in a world governed by all-at-once laws, right? Events at one time would depend on and be correlated with events at other times, but you wouldn't expect to separate that out into separate and independent directions of causality. It's just a symmetric mutual relationship. So what that means is that we would expect to see the future influencing the past and the past influencing the future in a kind of symmetric reciprocal way. So we have something like retrocausality there because the future does influence the past, but you shouldn't expect to be able to separate that out into two distinct and independent arrows of causation. So why does this distinction matter? Well, it matters because as soon as you try to write down a model which involves two distinct and independents of dynamical of causation, you run into a whole bunch of problems. So first off, it's not even clear how you can even get started with this kind of model, because you want to have the future produce the past, and you want to have the past produce the future. So where on earth do you start? Where does this whole process begin? It seems sort of that it can't begin at all, and the whole process can't get off the ground. Now, there is a possible way around that, and it's going to require a little detour into some time travel stories. So if you enjoy time travel stories, you might have noticed that there are kind of roughly two different types of time travel stories. In the first type, time travelers can't change the past. So they can go back into the past, but whatever they do in the past has already happened, and therefore the actions that they take won't change anything. They remain in the same timeline, and when they go back to their present, it's still the same. So for example, an example of that occurs in Harry Potter and the Prisoner of Azkaban. On one fine evening, Harry and his friends see some weird things happening, and it later transpires that this happened because a later version of Harry travelled back in time and got up to some hijinks. But the important point is that those events already happened the first time round, so time-travelling Harry didn't change anything. He remained within the same timeline. The alternative is mutable timeline time travel, where the time travellers can change the past. So an example of that occurs in Back to the Future, where Doc and Marty go back into the past and interfere with his parents' love life, and when they get back to the present, it's a different present. Some things have changed. So those are two quite different ways of thinking about how time travel might work, and they translate into two different ways of thinking about how retrocausality might work as well. You could imagine retrocausality which doesn't change the past because it's already fixed from the start, and that's indeed what you would expect to see in the kind of all-at-once approach. But in a more dynamical approach, you could imagine retrocausality actually changing the past. And that provides a way to kind of get the process of dynamical evolution off the ground in this retrocausal context, because you can imagine, say, starting at the beginning of time, evolving forwards for a while, and then at some time, an action is taken which has a retrocausal influence, and that retrocausal influence sort of reaches back into the past, adjusts some things, and then those changes are propagated forwards in time such that they change the present, and then more changes can happen further into the future. So that approach at least allows us to kind of get off the ground and start this retrocausal model working. But then there are other problems we are going to run into, because it's quite well recognized that time travel which changes the past leads to a whole bunch of logical paradoxes. The most famous example is known as the grandfather paradox. And in the grandfather paradox, we imagine a time traveler who goes back in time and for some reason decides to kill her own grandfather before the grandfather can have any children. So then, of course, the time traveler is not born, but then, of course, she can't go back in time and kill the grandfather. So there seems to be no logically consistent way of reconciling all these events, and we have a paradox. And those kinds of paradoxes, we will run into those kinds of paradoxes more or less inevitably in any dynamical retrocausal model, because the point of those kinds of models is that the arrows of causation are separate and independent, and if they are separate and independent, then they can come into conflict. So it seems more or less impossible to come up with a dynamical retrocausality model which doesn't run into all these problems. And the grandfather paradox idea is perhaps somewhat far-fetched, but one can imagine similar examples using retrocausality, which would also lead to paradoxes. So, for example, Tim Maudlin has suggested what one might regard as a quantum version of the grandfather paradox. It's a specific experiment which is arranged in such a way that if you try to give a retrocausal interpretation of the quantum processes going on there, it looks as if you end up running into a similar grandfather-style paradox. And therefore, Maudlin has argued this shows that no retrocausal approach to quantum mechanics can be consistent. But the thing is, all of these kinds of objections apply specifically to dynamical retrocausality. All-at-once retrocausality, on the other hand, doesn't have these kinds of problems. And that's because in an all-at-once model, the point is that the whole thing is adjusted at once in a mutually consistent way. So you can't get contradictions like that. One can imagine, for example, all-at-once laws, which simply assign probabilities to entire courses of history. And since each course of history is, by definition, self-consistent, you're never going to end up with contradictions or paradoxes in that kind of picture. So Maudlin's argument actually applies specifically to dynamical retrocausal models of quantum mechanics, but all-at-once retrocausal models of quantum mechanics are absolutely fine. So that all looks quite good for the people who would like to who would like to get rid of non-locality by using retrocausality. But there is a catch, because these kinds of all-at-once models of retrocausality are really not local themselves. So what I mean by that is that in these kind of models, because they assign probabilities to entire courses of history, there's no reason why an event at one point in space-time can't depend on an event anywhere else in space-time. Indeed, you would generically expect that events in various different places would depend on events everywhere in space-time. So for example, if we imagine the Sudoku grid is a world populated for some reason by purple and green socks, then we can get non-local effects in this world if, for example, we make a law which assigns probability 0 to all configurations of the socks, where the sock in the top left corner and the sock in the bottom right corner have the same color. So that will give a non-local effect, right? If I observe the sock in the top left corner, I know at once what the color of the sock in the bottom right corner must be, even though there's nothing traveling in between them or communicating in between them. We can, if we want to, put things in our model traveling between various points carrying information, but those things are superfluous. They're not really doing anything. The probabilities here are doing all the work, and thus locality this kind of model isn't really local and certainly doesn't need to be local. So this seems like a pretty big problem for the strategy of trying to use retrocausality to recover locality, because essentially it seems like the only really consistent and coherent approach to retrocausality is this all-at-once picture, but the all-at-once picture is non-local anyway. So this strategy seems like it's going to run into problems. Furthermore, I also want to argue that some of the motivations that people may have for wanting to restore locality are in fact not adequate. So one of the main reasons people think it's important to try to recover locality in quantum mechanics is because they believe that non-locality is inconsistent with relativity, with Einstein's theory of relativity. And so what they mean by that is that Einstein's theory of relativity says that there's no fact of the matter about whether events are happening at the same time if they're happening at different locations. So different frames of reference, that is, people moving at different speeds, will draw different conclusions about whether events are happening at the same time or not. So here in this experiment, we can see different frames of reference, and there are sort of different possibilities for what could count as the same time in London and Sydney, depending on your frame of reference. So if you think of non-locality in the sense that when a measurement is performed on the particle in London, that has an instantaneous effect on the particle in Sydney, and the particle in Sydney changes its state in some way, then you do indeed seem to have a problem with relativity, because how do you know at what moment the state of the particle in Sydney is supposed to change? You can't pick any of those moments because relativity tells you that none of them is really the one moment that is the same time. And so there's kind of a symmetry there which you would have to break if you want the non-local influence to happen at the same time as the measurement. But non-locality doesn't have to look like that in an all-at-once picture. There's no reason why the measurement in London has to cause an instantaneous change to the measurement in Sydney, because we can have our measurements in Sydney and London standing in a symmetric reciprocal relation with each other, which entails that they are adjusted in such a way to be consistent with one another, but there's no sort of instantaneous change to the particle. The effect of one measurement is seen when the other measurement is made, whenever that measurement is made, and it doesn't matter when it's made. So this particular motivation for trying to get rid of non-locality, I think, doesn't really go through because it assumes that there's only one possible way to implement non-locality, but there are, in fact, other possible ways of implementing non-locality which would not be inconsistent with relativity in the same way. Another key motivation for wanting to restore locality to quantum mechanics is simply based on the observation that the world as we ourselves experience it seems very local, right? You know, I can't just click my fingers and make things happen in Sydney. If I want to influence events in Sydney, I have to do something boring like write a letter and send it through the post. So our experience is that things are local. We can only influence circumstances in our direct vicinity, and there are only very rare exceptions to this, which are seen in sort of very special quantum mechanical experiments, but most of the world appears local. So the question is, if quantum mechanics is really non-local, why does the world seem so local to us? Where does all this locality come from? And the thought here is that, well, a good explanation for the fact that the world mostly seems local is that it really is local, even at the level of quantum mechanics, and so we should try to figure out how quantum mechanics can be made local. And this argument, I think, sort of works until you introduce retrocausality into the picture. Because, of course, the whole point of introducing retrocausality was to allow us to produce effects which look a bit non-local, even though they are in fact local and everything is mediated by physical systems traveling at various places in space-time. And so what that means is that once you add retrocausality into the mix, the fact that the underlying microscopic world is local in this sense actually does nothing at all to explain why the world as we experience it seems to be so local, because retrocausality can be used to produce effects which look extremely non-local. So as you recall, I said that quantum mechanical non-locality can't be used to send signals. But of course, if we had access to unrestricted retrocausal processes, we could send signals faster than light, or appear to send signals faster than light, because we could just send our messages into the future and then get someone to intercept them and send them back into the past at the appropriate time. And so it would look as if that message has traveled faster than light from somewhere to somewhere else. So introducing retrocausality immediately makes locality useless as a way of explaining why the world seems so local, because locality plus retrocausality can still lead to these very non-local effects. So in this kind of model, if you want to explain why the world appears to be so local, you still have to add something else, right? You have to do something like constrain the set of retrocausal influences in such a way that they can't be used to create effects stronger than the quantum mechanical correlations. And therefore, it's really those constraints that are doing all the work in your explanation. The locality itself is of no value to explain these things. It's whatever else you added that is doing the job. So again, I think this motivation for wanting to recover locality doesn't really stand up when you examine it. The final motivation is that I think that a lot of that people would like to restore locality because it would allow us to think about the world in roughly familiar terms. So often in physics, when we talk about fundamental things, we tend to use tend to describe them in terms that are quite familiar to us from our everyday lives. So we'll often talk about particles or waves, or perhaps less familiar about fields and these kinds of things. And these are all things that we sort of have reasonably clear mental images of, and we sort of feel that we understand them and can conceptualize them. And the point is that all of these things are kind of known for traveling locally. That's kind of what we think of them as doing. So particles travel along continuous paths in space-time, and they don't interact unless they kind of collide like billiard balls or whatever. And similarly, waves, you can see them traveling continuously through whatever the medium is. They don't interfere until they pass through each other. So all of these things are quite local. And so it seems, so if we would like to conceptualize the world in these familiar terms, it seems tempting to try to make quantum mechanics be local so that we can conceptualize the world in a way that seems familiar to us. But this, I think, is just not very good scientific practice, and we shouldn't decide in advance what we think the world is made out of and then try to massage the science to be consistent with that. We should be looking at the science and asking, what does it tell us about what the world is made out of? So, I don't know what the world is made out of, but probably not particles, waves, and maybe not even fields. So again, I think this is not really a very good motivation for wanting to restore locality. So to sum all that up, I don't think that the argument which aims to use retrocausality to restore locality succeeds, and I also don't think it was a very good idea to try to restore locality in this way anyway. With all that said, I do in fact think that quantum mechanics is telling us that the world is retrocausal. So I now want to give you a different argument, which rather than trying to get rid of non-locality, in fact assumes non-locality from the start. And I want to argue that if we assume that, we in fact get the conclusion that there is a retrocausality in a certain sense. So as I say, we're going to assume, we're going to go back to our Sydney-London experiment and assume that the correlations between the particles in that experiment do indeed arise from some kind of direct non-local influence between those events. So the thing is, this setup can be made entirely symmetric, right? We can prepare the particles such that they look exactly the same. We can have the set of measurements be exactly the same. We can have the measurements be performed at times such that they are at the same time in some reference frame, and we will then get statistics that look exactly the same on either side. So there seems to be nothing in this experiment, in the evidence that it gives us, to justify the conclusion that there's a causal influence from London to Sydney or from Sydney to London. If we're going to explain this experiment in terms of a one-way causal influence, we then immediately have to kind of break the observed symmetry and just add in a direction which we have no empirical justification for. And that seems like a bad thing to do scientifically. If all the evidence is telling us that this is perfectly symmetric, we should respect that in our account of what's going on here. And therefore, it seems to me that the only consistent way to think about that is to say that there is a two-way influence between these particles, that there is a mutual reciprocal influence between them, rather like the influences that we saw in our Sudoku grid, where there was no directed causation in either way, just a symmetric reciprocal influence. But the thing is, we can do exactly the same experiment in a way that has the particles separated in time rather than space, right? So instead of sending my second particle to Sydney, I can just keep it here in London. So we'll do one measurement, we'll wait a couple of days, and then we'll do the next measurement. It turns out that if we do the experiment that way, we get exactly the same results, right? Statistically, those experiments look exactly the same. There's no discernible difference in the experimental statistics if the measurements are performed at a space-like separation or a time-like separation. And so again, by the principle that we shouldn't break symmetries if we can help it, it seems that since these experiments look exactly the same in every way, we should assume that the underlying structure is the same, right? We should say that whatever causal structure is happening in the space-like case is also the causal structure that is happening in the time-like case. So it seems like, again, in this case, we should say that there is a mutual reciprocal symmetrical influence between these two particles, even though one particle is in the future of the other. So what that means is that we do have an influence from the past to the future, but also an influence from the future to the past, because these measurements stand in this mutual relationship. But I think clearly this kind of retrocausality is not the two arrows colliding retrocausality. This is an example of the kind of all-at-once retrocausality that I was discussing. So what this seems to be saying is that, yes, we do have, in a sense, we do have instances in quantum mechanics where the future influences the past, but not in the sense of a distinct and independent arrow of causation coming backwards in time. It's more like a sort of symmetric reciprocal adjustment across different times. So that is my answer to the question with which we began. Yes, I think that quantum mechanics is telling us that the future influences the past, but not in perhaps the way that some other physicists might suggest. And that, I think, is very interesting. The idea of the future influencing the past, and for more broadly, this kind of all-at-once picture of lawhood is quite different to the way that we have thought about many of these things in physics and philosophy in the past, and there are many interesting questions about what that means for things like our understanding of causation, of what laws are, of free will, all these things. So those are some of the things that I explore in my research, and I'm happy to talk more about them. But that having answered the question, I should perhaps stop talking and see if we have questions for you.
So I would like to ask you if you have questions to use the microphone so that this can be recorded. I see a first question here.
break the ice. I actually have a substantial question. So let me put it this way. I think I listened very carefully, and I heard you other times mentioning these things. And I think everything you say I find it convincing, completely convincing. I mean, exactly every single phrase. It leaves me with one open question, which I want to mention, and I want to say where I think is to be searched the answer to this question, and therefore, in a sense, what is missing in the overall picture, which is the following. The question is, all right, so I buy everything you say. At the end of the day, I'm convinced, okay, fantastic. So quantum theory, and therefore also classical theory, which is a consequence of that, I should think in this way. So there are correlations, and I can call it influences, or I can call it in another way if I want another name, between past events and future events that in some sense determine one another, because there are relations between them which are of the kind you have discussed, and the temporal one are that which you're suggesting, the same kind of the spatial one. It's fantastic. So why we usually say we influence the future, and we don't say we influence the past? So I think what you've said captured exactly the way the world is, except for one detail. That is what you started from. Say, well, it seems obvious that we influence the past and not the future. So where does this fit in? And it seems, so that's the question. And it seems to me that there is no answer to this question as long as we just look at the equation of mechanics or the equation of quantum mechanics. One has to look at macroscopic systems. One has to look at the real world in which there is a macroscopic decision of thermodynamic, and there's an arrow of entropy, and there's an arrow of time. And therefore, every time we say we influence in the future but don't we influence the past, we're not talking about mechanics. We're not talking about the laws of the amplitude probability of quantum mechanics. We're not talking about the laws of motion. We're talking about something else. We're talking about how things behave thermodynamically, probabilistically. And just to close, at some point you said the funny correlations the quantum mechanics gives, if there were just correlations, we wouldn't worry because you thought the socks, we understand why there's a correlation. There's a common cause in the past. Okay? So why do we look for it in the past? And the idea of common cause in the past was long discussed by Reichenbach. And in fact, is very often associated with the name of Reichenbach. And in his book, The Direction of Time, Reichenbach says the principle of common cause is not a principle, it's a theorem. It's a consequence of the second law of thermodynamics. So it seems that that's where could be a way of... would you agree with that, with all this? Or I add a lot to what you're saying.
Yeah, I'm glad you asked this question because I've been working on exactly this recently. So the question of, why is the past inaccessible in a way that the future is not? Yeah. So I do think thermodynamics is part of the answer, but I think it's not the complete answer because the other part of the answer is to do with the fact that the whole history as selected by these all-at-once laws needs to be consistent, right? You can't have contradictions. And if we could, move into the future and then cause things in the past, that would lead to contradictions very easily. So the causal structure of the world needs to be arranged in such a way that if you're moving forwards in one direction, you keep going in that direction. You can't use your actions as inputs into processes that are going in the wrong direction. So basically, I think that the causal structure is arranged in such a way that once you start going down it, you have to keep going down it in the same direction forever. So the question is just where does the direction come from? Why are we going this way rather than that way? And the answer to that, I think, is thermodynamics. Thermodynamics puts us into the flow in this direction, but it's then the need for consistency that keeps us going in the same direction. And indeed thermodynamics itself relies on the sort of continual flow of influences in a single direction, because otherwise you would get things looping around and you wouldn't be able to get a sensible arrow of thermodynamics either.
So it seems to me that this question has a softer version. As in, okay, one question is, why can't we influence something in the past? And another question is, why can't we just see the future without necessarily influencing it? So what do you think about that? In a sense, right, why isn't future accessible to us in that sense, in the sense of just seeing it, and the past is somehow?
Well, the future, I mean, to some extent we can see the future in the sense that we know some laws, and the laws allow us to make predictions about the future, and the predictions are not perfect because our knowledge of the laws is not perfect and our knowledge of the initial conditions is not perfect, but we do have some insight into what is going to happen. The reason why we have different insight into the past and into the future is, I think, mostly down to thermodynamics and the fact that sort of memories are stored and records are formed in a certain direction of time, and that's what kind of gives us our direction through this causal flow that I talked about, the need for consistency, and it's the build-up of the fact that memories are formed in this direction which puts us in that particular direction.
This is moving a little bit away from quantum mechanics, so I understand if it's kind of not hugely relevant, but in terms of time travel situations that rely on closed time-like curves, does that come under the umbrella of dynamical or all-at-once retrocausation, or is it some other conception? Is the best way to see that?
So I think you would have to think about them in an all-at-once way, because there's various different frameworks people use to do physics sensibly on closed time-like curves, but they all involve some kind of global consistency condition. Like, you can't just start at one point and evolve independently around. You'll get contradictions if you do that. You have to impose some kind of consistency condition. I like the way they do it in the process matrix framework, but there's various other approaches as well. But all of those approaches do involve thinking about the whole thing at once, right? So that is very easy to make sense of in an all-at-once picture, but a dynamical picture won't really let you do that, because you do have to start at one point and be independent of what's happening everywhere else in that picture.
So this might be a kind of crazy question. In the story of your life or Arrival, there's Ted Chiang imagines an agent who experiences time in a completely different sense.
Yeah.
So do you think that is physically possible, or do agents have to have the sort of properties that Carlo was describing to them?
I think it would, yeah. I met Ted Chiang this summer. It was really cool. So I think it would be possible if the agents were not able to intervene, because obviously if you can see the whole of history, then you can easily create paradoxes by intervening to change things. So basically, everything...
So you should maybe say a little bit more about what the agents are like in the story, because I don't know if everybody...
Oh, I'm trying to remember.
I mean, they sort of experience time all at once, so they...
I mean, I guess I've already spoiled the movie, but anyway. That's aliens sort of arrive, and they kind of see the whole of rather than moving forwards through time, they have this very different type of experience where they see the all-at-once picture that I've described. But yes, and in order to make that consistent, it seems to me you'd have to have those agents only knowing things and never being able to intervene or create changes, because as soon as you do that, you then run into consistency problems. Basically, you shouldn't be able to change any part of history that you already know about for sure. So yeah, I mean, those agents could exist, but I guess we wouldn't know about them because they would not be able to intervene or communicate with us.
I have a question. So retrocausality in quantum mechanics is something that is today exploited also, I mean, in precise interpretations of quantum mechanics, and goes beyond this because it's also used in experiments and so on. When I look at the formalism, my impression is that the formalism is very similar to that of quantum field theory.
Yes.
So it's like a step between quantum mechanics and the relativistic version of quantum mechanics that is quantum field theory,
Yeah.
where in fact you have particles that propagates, but every time you compute the probability for a particle to propagates forward in time, you have also to include the probability of the antiparticle to propagates back in time. So in which sense what you are describing and thinking about is just this inclusion of more quantum field theory, so something that a theory that is already established, that is already, we know that it's already working into the simpler framework of quantum mechanics, or is there anything more that we have not understood yet there?
Yeah, so I think these kind of intermediate-ish theories with particles propagating forwards and backwards in time are, in a sense, a mistake, because I think they are kind of misconstruing what retrocausality has to look like, because if once you move to this all-at-once picture, then, as I said, you don't really need particles to travel places to communicate information. You have that already built into the probabilities. So I think that quantum field theory, insofar as it incorporates that kind of approach, is a better way of thinking about that. I mean, quantum field theory does sort of build in causality requirements. So in most versions of it, they don't sort of allow you to intervene at some point and cause things in the past. But it's a little bit unclear because I guess the measurement theory of quantum field theory is quite conflicted. So arguably, there could be versions of it where performing a measurement could cause things in the past. It would depend on exactly how you resolve the issues around what the measurement theory looks like.
Any more questions from the public? Even questions about, again, time travels? Time travels in fictions?
This spooky action at a distance that apparently exists, how big are the distances that they're looking at?
No limit. It's as big as you want. In practice, in real experiments, it's quite difficult to preserve the entanglement, and so what we can create is sort of limited by our technological capabilities. But there's also sort of natural entanglement, which can be as big as the universe in principle. So yeah, no limits at all. Because it's not sort of...
That's being tested with satellites.
Yeah, with the experimentals done
Hundreds of
to
kilometers.
orbit.
Yeah, exactly. So
Thousands of kilometers. The Chinese them.
Yeah, no. Emily, do you want to add about Zellinger with satellites or?
go ahead. Yeah.
I think got the Nobel Prize for that.
Yeah. Exactly.
Yeah, so the first these were things were tested in a laboratory at distance of meters, then they did between...
I can't hear. Yeah.
Oh, sorry. First it was sorry? Yeah. First it was tested in laboratories at distance of meters, these correlations. This is the Nobel Prize, the last week Nobel Prize. This week Nobel Prize.
This very week,
ago.
yeah.
Tuesday. Zeilinger, who is the third Nobel Prize winner, did an experiment in the Canary Islands from one island to another, some tens of kilometers. But then, and that's he got the Nobel Prize, that's quoted in the Nobel Prize motivation. But then with the Chinese, he did a quantum correlation between photons in a satellite and down in some base in China, which is a distance of the height of I don't know, how high is the satellite, I don't know. 100 kilometers probably, the ones they used. So as far as has been tested, the correlation is always there.
That's kind of what has seemed so spooky about it, right? That the distance doesn't matter at all. The particles know what's happening just as well, no matter how far away they are.
Yeah, and if I can add one thing, because that's my subject of research, what we are doing today in cosmology with the study of the universe is the idea that, so if particles have been together in the past of the universe, now past and future, it's a confusion now. Okay, so if particles were together in the infancy of the universe, then they can still be presenting correlations later. So what we study now in cosmology are, in fact, those correlations, so the same measurements at faraway places in the universe, and we understand this as being caused by the initial entanglement between those particles in the primordial universe. So that's quite mind-blowing. So if you want, everything that exists in the universe is because there is such a spooky action at distance, such an entanglement.
I'm a civilian. No, I look at what you've discussed, and I ask myself, so what are the implications on our lives? What about the Big Bang? Is that what happened? So I mean, that would be interesting to understand. So you've talked about this. What are the implications for, for the world that we live in?
So sort of this in and of itself, this is kind of just a reinterpretation of quantum mechanics, so it doesn't predict anything new. But I guess my opinion is that thinking correctly about quantum mechanics is hopefully going to help us as we try to move beyond quantum mechanics and as we do the next theory. So, I don't know exactly how that will work, but kind of my motivation for trying to understand quantum mechanics better is that thinking about it better will hopefully allow us to do better science in the future, and that will presumably have technological implications, or will it change our understanding of the early universe and the Big Bang and all those sort of things. So, I do believe that there will be implications one day, but I don't at this moment know what they are.
Well, even though retrocausality, according to some people doing experiments with quantum mechanics, is a better way to understand some phenomena in the lab. We may agree or disagree, but...
it doesn't right now predict anything different from quantum mechanics, but I think it makes things easier to understand in certain situations.
And the quantum mechanics is the basis of everything we use, all the technology we use. So, of course, it has an effect in our life. Somebody who hasn't asked any question. Otherwise, because otherwise I have to go back to somebody who has already spoken, and better to include more people in the conversation.
Thank you very much. Just, again, another civilian like our friend up there. When you're talking about the observations and the experiments being made, what is the relationship between the particles? Like for your Sydney to London experiment, what makes them so special in which they can do this type of communication, if you will?
Right, so what happens is that before we send them to Sydney and London, we prepare them together in a special kind of joint state. It's called an entangled state, and it's basically a state of two particles where they're not independent from each other anymore. They can't really be separated into two distinct states of the particles. So that preparation has to be done while they are physically together, but then they can be separated and sent off to different places, and they will still be related to each other in the same way. So we will still see these distant correlations from this kind of special joint state, even though they're now very far apart.
So are they essentially like clones, or are they like pieces of the same, or are they completely identical?
They're two distinct particles, but they will usually be indiscernible, so identical. You can't tell them apart. But they could come from different sources, and we just prepare them in a certain way, or we could arrange for the right kind of source to produce them together in a pair. But yeah, they are two different particles, but indistinguishable from each other.
Yeah, a question, comment, or a provocation. because I found very inspiring everything you say. You started off at some point, and you said at some point, well, of course, we influence the future, not the past. And then another moment you said, well, of course, we learn physics. Physics is about some equations that tell us, given the present, what's going to happen next and next and next and next toward the future. It seems to me that both what you've been saying very clearly and that other sense, sort of related to that, the entire history of mechanics in the last 2 centuries, is telling us that, no, that's not the right way of thinking about nature. Okay, the right way of thinking about nature is that there are correlations between events, and we can write down these correlations, and these correlations don't distinguish the past from the future. Good. So then, it seems to me that what is interesting here is not that it closes a problem, but it's super interesting that it closes this problem. What it is open another problem.
Right.
Which is good. So now we have something that we view as obvious, but it's not obvious, it's a thing to be explained.
Yeah.
And that's a fantastic research program. Why? Most likely, I think, I don't see anything else, for thermodynamical reasons, it happened that we influence the future, not the past. And why it happened that we remember the past and not the future, and we think in terms of evolving thing and so on and so forth. Would you agree with this?
Yeah, I mean, I think a lot of things, both in philosophy and physics, have been kind of predicated on this picture of take an initial state and evolve things forward in time. And I think, as you say, there's now very strong evidence that that's probably not the right way to think about things. And that means that a whole bunch of things, both in philosophy and physics, need rethinking and reconceptualizing in the light of that quite different way of seeing the world. You know, how should we think about laws of nature now? How should we think about causation? All of these questions need to be, I think, readdressed in the context of this different approach. I think it's where physics in particular is in a slightly awkward position because I think many physicists do recognize that this time evolution picture is a bit naive and not the way things really work, but it's still quite deeply rooted in the way we think and talk about many things, and we haven't totally figured out how to transition away from it. So I think there's a lot of things in physics as well as in philosophy where we benefit from kind of picking out the threads of what is coming from the time evolution picture and what is really the evidence and how to separate those things.
Yeah.
So I guess I'm not officially a civilian, but I'm not a philosopher of physics. I was wondering if you could say something about what the implications will be for free will.
Yes. Well, I think it's interesting because I mean, there's many different ways that people have phrased the problem of free will, but one of the problems of free will is the idea that like nothing you do is free because it was all predetermined way in the distant past, right? The past produced your actions. And if you move to this picture, that particular problem seems less severe, right? Because now it's no longer the case that the past produced your actions and not vice versa. You in the past stand in this more sort of symmetric, reciprocal relation. So I think there's a sense in which perhaps the issue of free will is not as bad because it's not as though there's no longer this asymmetry where the past causes everything. Rather, your actions cause the past just as much as the past causes your actions. So there's perhaps a more sort of participatory way of seeing the action in that kind of picture. This is a thing I'm working on at the moment, so I haven't fully formulated that answer, but I do think it does perhaps change the way we would think about free will, at least in the sense of not everything is predetermined, perhaps.
But if I can interject this conversation about this topic, so what you are describing here in relation with quantum mechanics has a counterpart in the block universe. That is also, in general relativity, the idea that everything exists all at once. Mm-hmm. And there is the same question there about free will. What about free will in the block universe? Well, the way out of the conundrum is to realize that we don't have a picture from the outside of the universe. We always see a picture from within. We are observers with the partial visions, and we move in this universe having our partial view. Would you agree that, I mean, with quantum mechanics, there is exactly the same thing. There is the importance of the observer and these partial views. Maybe, would you?
Yeah. And as I say, I think free will is, I think some people have the idea that the block universe makes problem with free will worse, but I think the opposite. I think the block universe makes free will better because it's no longer, you don't just attribute everything to the distant past all the time. And so you do have this option of taking an internal view and sort of seeing your actions as the source of everything else.
That's very nice.
Thinking on that, where free will, you've expressed that it seems that it becomes a loop. So once that becomes a loop, where does retrocausality begin then?
So that is kind of the reason for going to the all-at-once picture rather than the two arrows picture is precisely that you don't have to pick a beginning point. It's like in the Sudoku grid, right? You can begin anywhere. Any beginning is equally valid. There's not a sort of prescribed starting point, and any way of filling in that grid will produce the correct solution. So that kind of the idea of this all-at-once picture is that the question of where does it start is just the wrong question, because that's not how things work in the all-at-once picture.
Yeah, so I guess connected to that, we've heard a lot of talk about both the past and the present, but I haven't heard, or the past and the future, but I haven't heard a lot about the present just yet. And I was wondering where, or if that shows up in the all-at-once picture, like where are we now?
Yes, I mean, I think of the present as sort of a relational fact, right? The present is present relative to me at this moment of speaking, but there are other versions of me elsewhere which have different presents. The present is essentially a perspective, right, on all of history. I happen to be located in this place seeing history from this point in time, and there are other people and other versions of me seeing different perspectives, and the present is a way of sort of capturing what my temporal perspective is.
Well, this was one, two. Yeah.
Civilian number 3.5, I guess. This isn't necessarily a question because, I mean, a lot of this is also over my head, but I don't know if anyone has seen the movie Everything Everywhere All at Once.
I have seen that, yes.
But as you explain it, for me as like an artist brain, that's what I relate it to. So if this is also over your head, that movie is incredible. And it might give you some insight, I guess, into what you're describing. So that's how I relate this information to something more visual, I suppose. But if that makes sense, if that actually has any reference to this, but...
Well, Everything Everywhere All at Once is kind of based on a related but different physical theory, which is an interpretation of quantum mechanics called the many worlds interpretation, where the idea is that at every quantum measurement and basically every event, the world just splits into all the possibilities. You get this huge network of like an infinite number of possibilities from all the different ways things could have gone. So yeah, it is kind of a similar idea, but it is, I think, quite specifically based on the Everett or many worlds interpretation of quantum mechanics, which is another way that people have tried to get rid of non-locality, in fact.
That's a beautiful movie. Even if you...
I saw it twice. So I'm just like, I need to make sense of this again.
Yeah.
It's like watching Interstellar.
Does it make more sense the second time round?
You miss things and then you pick it up. And I'm sure I could watch it like 20 more times.
So when you watch movies, sometimes you have to use the suspension of incredulity. And for me, watching that movie, it's a fantastic art experience, even though I don't believe the many words interpretation. Well, on the movie advices, I think it's a good note. Thank you, Emily, for your talk. Thank you, Emily, for all the good advices about movies.
Thank you for coming.